Okay, so for this problem, they want us to find the steady state solution of the system. So what that translates into is really finding the particular solution for this problem. So they want us to find the yp of t. So to find that yp of t, we're going to have to first go through and make sure that we avoid any linear dependence issues. And so we need to first take a look at forming the spring mass equation and then solving it to get a general solution and then building the particular solution. So first thing to do is recall from before our equation for the spring mass, which is m times y double prime plus b times y prime plus k times y equals f of t, our forcing term. So what you want to do is now look at what was given to us in the problem. And it's pretty clear they've given us the mass, which is 3 kilograms. They've given us the damping constant, which is 3 Newton seconds per meter, but they did not give us the spring constant or the stiffness constant. So we need to find that off to the side. So what we want to do is use a formula from physics which says that K is equal to the mass times the gravitational constant divided by the length of the spring that is being suspended at equilibrium. So the mass is equal to 3 kilograms, the gravitational constant is 9.8, and the length that our spring is stretched is 1.47. And this calculates out to be 60. So we're going to have a value of K equals 60 for our stiffness. So going back to our equation, we've got 3 times y double prime plus b, which is 3 as well, times y prime, plus k, which we just found to be 60 times y, is equal to 2 times the cosine of 2t. And so that right there is the equation that describes our motion for our spring mass. So the very first thing you always want to do is take a look at finding the general solution. So we're going to first set our forcing term equal to 0 and look at just solving 3y double prime plus 3y prime plus 60y is equal to 0. If you divide through by 3, that turns into y double prime plus y prime plus 20 is times y is equal to 0. And so to solve this, we need to look at either the quadratic formula or completing the square. So the auxiliary equation is r squared, and that was a single prime, by the way. So let's make that a prime again. So r squared plus r plus 20 is equal to 0. So r is going to be equal to -1 plus or minus the square root of 1 squared minus 4 times 1 times 20 over 2 times 1. So r is going to be equal to -1 plus or minus, looks like the square root of -79 over 2. So that's -1 plus or minus the square root of 79 times I. And each of those, of course, is divided by 2. So what's important to understand here is this would turn into exponentials. We would have an e to the -1/2 t, and then we'd have a cosine and a sine of the square root of 49 over 2t. And what's important to see here is that these values have nothing to do with our forcing term, so we know for sure that we have a linear independence. So when we form our forcing term, all we have to do is take a look at representing the cosine of 2t. We don't have to worry about any extra t's put in to watch out for the linear dependence issue. So our particular solution is yp of t is some unknown constant a times the cosine of 2t plus an unknown constant b times the sine of 2t. And now we can go ahead and find this by taking derivatives and substituting into the original differential equation. So we'll do that in our next video.